Hello everyone, welcome back to another example video. In this example video, we are going to be kind of doing a continuation of the last example video where we used the CSA Simplified Stability Analysis method to figure out the second order effects on this multi-story frame. Now, if you watched that last video, you will know that we actually didn't do the S-frame analysis in that video, and I said it would be in a different video, which is this video. So this video, even though it looks like it's going to be a hand calculation example, it's actually going to be the S-frame analysis of the structure so that we can get the bending moment and axial load required for the simplified stability analysis method. Another thing worth mentioning really quick is that since we talked about S-frame in detail in our single story frame analysis, the S-frame analysis done in this video will be rather quick. I won't spend as much time explaining things. If you guys want more explanation towards certain aspects of S-frame, I recommend you go watch the video where we did the single story frame analysis. But before we start, I just want to say I hope everyone here is doing well. I hope you guys are still excited about structural engineering. It's about this point where students start to fall off. So again, I hope that you guys are doing well. All right, let's jump into S-frame. All right, so once in S-frame, there's a couple little preliminary things we have to do before we start our model. The first is just give some description to the project so you guys can, of course, fill out whatever you want. Then you click next. It wants to know the input units. So being Canadian, of course, I go metric. If you're American, perhaps imperial, go next. The output units, of course, I'm going to stick with metric, next. Modeling tolerances, I'm just going to leave. And then, of course, the building codes. So, of course, these are the most current up-to-date building codes. I'm just going to go next. And then we are going to start a new model from scratch. So after here, we can go finished. And then we will be introduced into our modeling space. So if you guys remember from the last video, there's basically two different things we need to do. The first is define all of the geometry, and then we define the loading. So we're going to start off with the geometry, and we are going to create the two-story frame. Now, in order to start, what I like to do is I like to create my initial joint. So I'm going to go down to the joint tool right here, and I click it. And its initial coordinate, of course, is going to be 0, 0. So I'm going to have this as the bottom left side of the frame. So if I were to go OK, as we can see, it has now created a joint at the very bottom left-hand side of the frame. Or the right-hand side, you guys can do it however you want. But if this is going to be my bottom left-hand side of the frame, I'm going to put the first story column right here, which we know is 6.5 meters tall. So what I'm going to do is I'm going to define a second joint up here for this column. We know the X component is going to stay the same, but now we know that the second joint is going to be 6.5 meters above our first joint. So I'm going to go OK. And as we can see, we now have these two joints. But that's all they are right now. They're just joints. If I want to create the actual member between them, I come down one button to this member definition tool. I click it. And then by default, it has two joints already selected. So if I have two joints defined, which I do, I can click OK, and I can define a member between the two joints, just like this. So this is one way of defining members. If I wanted to, I can add a bunch of joints for the rest of my structure, and then use this command to join them all together to basically get my final structure. But one simpler way is once you have one of the joints defined, which we do, we can use this one joint command right here. Basically, it just takes a joint and it extrudes a member in very specific directions, which are here. So if I wanted to make the next horizontal beam, which is 10 meters long, I know that I'm going to have a beam in the positive X direction, and then its distance is going to be 10 meters. So I go positive X direction, 10 meters, and if I were to go OK, and now click on this joint, as we can see, it has now defined that beam for me. So we're looking pretty good so far. If we were to look at the second beam, which goes across the MRF frame, we know that it has a length of 10.5 meters. So I can change this from 10 to 10.5. I can go OK, and then I can click this joint right here to add that second beam. And then for the third beam, we know it's 10 meters long. So I can switch this back to 10. I can go OK, and I can click it yet again. So now we have a 10 meter beam, a 10.5 meter beam, and then a 10 meter beam yet again. The next thing I'm going to do is I'm going to create all of the columns for this structure. So the second story columns all have a length of 5.5 meters. And if I'm starting at this joint right here, we know we are going in the positive Y direction. So I'm going to go positive Y right here, and we know that the length is 5.5 meters. I can go OK, And if I were to click the joint, as we can see, our column is now defined. The nice thing too is that since all of these columns are the same for this joint, and this joint, instead of manually clicking each joint, which you can do, I can just highlight all of the joints I want to apply this member to, and it automatically creates all of my columns. Another nice thing is if I were to look at this beam, which runs across our second story right here, I have both of the joints already defined. So rather than using the one joint tool, if I wanted to, I can come back to the two joint tool, go OK, and I can just simply define members between the two joints. So it's actually nice and simple once you get the hang of it. Nice and quick. Oops, there we go. The last thing I need to do is I need to define the columns for the first story, which I already have a joint defined. So I'm going to go back to the one joint tool, but we know that in this particular case, in reference to this joint, our columns are going in the negative y direction. So I'm going to switch this to negative y, and we know that our columns are 6.5 meters tall. 6.5, I can go OK, and then I can highlight all three of these joints because all of the columns are identical. So from here we're looking pretty good. We have now defined our frame, but it's still going to lack a couple of things. First one is going to be the moment releases. We know that in our structure, only this center bay right here is a moment resisting frame. These two columns on this side and on this side, they are lean on columns because these two beams are actually hinged, or we release the moments. Now in order to release the moments on these beams, we just go down to this button right here, the member release tool, and everything by default is good to go. We just go OK, and then we select the areas we want to release the moment. So for both of these beams, we want to release it on both ends. So I can click here, as well as down here. And then on this bay over here, we want to release the moment on both ends of these beams. So I click here, I can click here, I can click here, and then finally here. So now we have most of our frame defined. We are missing two things. The first one is going to be the support conditions, and then the second one is going to be the section properties. We know that our beams in this structure are going to be different than our columns. So in order to define sectional properties, we just keep going down the list to this one right here. It's section properties tool. And if I were to click it, as we can see, I'll just put this to the side, we have no sections in our modeling space. In order to add sections to our modeling space, we come up to this button right here, Edit Section Properties. And if I were to click it, it appeared off the screen, we can see that we currently have no members. To add members, we just click some of these buttons over here. We can add custom members, or the nice thing about S-Frame is it has default members saved in its database. So if I'm looking for steel members, I can click steel over here, and it popped up on the other screen. And as we can see, we have all the steel members found in the Canadian CISC database. If you're American, they have the American database, AISC right here. So no matter where you are, you're basically good to go. Now by default, it'll give you all of the W-shape sections. If I want an angle or an HSS section, I can just click whatever I want on this side. But we know that we are basically dealing with two sections in this example. The first one, our beams, are W460 by 97. So all I have to do under section name is go down and find our W460 by 97. So W460, perfect, 460 by 97. As we can see, S-Frame has all of the data related to this beam based on CISC. And to add it to our model, we just have to go add to. So down here is all the beams that are going to be imported into our model. So this right here was just the beams. If we wanted the columns, which are 310 by 97, we just find it in the drop-down menu. So I come down, 360, there's the 310s, 310 by 97. I click it, it has all the properties. And again, I just go add to. So again, these are the members that are going to be added to our model. Once you have all the members you want, you can just click OK. And as we can see in our model, we now have two members. Now, if you remember from the last video, by default, both of these members are going to be defined as a black color. It makes it very hard to tell the difference between the two. So what I like to do is I like to give some colors to the members so we can see which ones we're dealing with. So let's take our beam members and make them pink. And let's take our columns and make them blue. Once we've assigned the colors and imported the sections, we can simply close this menu. And as we can see by default, S-Frame will assign the first section to every member in the model. So everything right now is a W460 by 97. We know though that this is just our beams. Our columns that we want are W310 by 97s. So in order to do that, we simply just click on this section. As we can see, it's now kind of highlighted. And we can just click on the columns we want to assign this to. So we can click on the columns, or if we want to, we can highlight multiple columns. So if I want to, I can drag this across, but if I'm going left to right, nothing will happen. If I go right to left, it will assign the section. If I want to highlight something left to right, I have to select the entire member. So in this case right here, I do have the entire column selected. It will indeed add that section. But if I want to go right to left, anything that it touches, it will now become that member. So I don't have the entire column selected, but since I'm touching it, it'll change it over. So I can add this to all of the columns that I want. And now we can see that everything blue is our columns, which are W310 by 97, and everything pink is our beams, which are W460 by 97. Nice and simple. The last thing that we need to do in terms of geometry, of course, is adding the support conditions down to the base of our structure. So to do that, we just keep going down the list of buttons to this one right here, which is our support tool. So by default, S-frame will have it as a fixed connection. As we can see, the translation in X, Y, as well as the rotation about Z is all toggled on. So if I want to make a pin, I would simply not restrict any rotation about X, so just the translations are restricted. I can go OK, and then I can click the joint. If you want to, you can also highlight the joint. It'll apply the support. Now these two supports right here are fixed supports. So if I want to create a fixed support, all I have to do is restrain the rotation. As we can see now, all three are toggled on. I can go OK. And the nice thing about S-frame, of course, is I can select multiple joints at once to make my process a little bit easier. So from here, we are actually looking pretty good. We have completely defined our frame. Now you guys may be wondering, hey Clayton, what happened to our moment releases? Well, keep in mind that every time you go to a different button, it's only going to show what's relevant to that button. For example, if I were to go back to my member definition tool, all of my supports are now gone. If you want to see what you've defined across any button, you can toggle them on down below. So for instance, I can toggle on my supports, I can toggle on my moment releases, I can see absolutely everything I need to. Now this is great because at this point right here, I have now completely defined the geometry of my frame, and I can start getting into the analysis portion of this. Now if we are doing the simplified analysis in CSA S16, we are going to do two linear static analysis, one for gravity loads and one for translational loads. So I'm going to come down here to my loads tab, and then from here I can create my gravity load analysis by going to this button right here, which is new load case. It popped off on screen, but what I can do is I can bring it back and it says load case description. Let's just call this our gravity load case. These scaling factors we don't really need to worry about right now, as we discussed in the last video, so I can just click OK with everything default. So now that I have a gravity load case, I can apply all of my gravity loads to this frame. Again, if you guys want to see the support conditions, you can toggle them on down below. So I can click here, same thing with moment releases. So for the gravity loads, we have two uniformly distributed loads on the first story as well as the second story. So in order to add a uniformly distributed load, I come down here to global load. I want it uniform in the Y direction, and then I just have to specify a magnitude. So since it's going downwards, of course, we have negative. And then for the first story, we know that our load is negative 55 kilonewtons per meter. I can go OK, and then I can apply it to the members just by simply clicking the members. Good to go. For the second story, we know that the load is a little bit less. It's negative 45. So I can just switch this to negative 45. I can go OK, and then I can apply it to our story. Now here's going to be one little trick to this multi-story example. CSA says that in order to prevent any inherent sway effects, we have to restrain this frame from basically any lateral movement. To do that, we have to add a roller to the frame at the ends. So what I would do is I'd come back to my geometry load case, I'd go back to my support conditions, and I just want to restrain lateral displacement. I can toggle both of these to off, so it's just lateral displacement. I can go OK, and I can highlight the two ends. Now this is where it gets to be a bit of a special case and a little bit of a trick to students. If our frame is symmetric, and if we look right down the center of this frame, it definitely is symmetric, these lateral reactions should be equal to 0. All right, so again, if the frame is symmetric both in terms of geometry, stiffness, and loading, these support reactions are going to be equal to 0. I want to tell you guys that because if you were ever to do this by yourselves and you notice that the frame was symmetric, you actually don't need to add these rollers. Now you guys are saying, okay, Clayton, that doesn't sound too bad. If it's symmetric, these are equal to 0. What I'm going to do is I'm going to continue the analysis with the rollers because something funny happens, and I guarantee it's a little trick that gets a lot of students. So if we look here, we have our rollers. We now have our complete loading for our gravity analysis. We are actually good to go to run the gravity analysis. So to run an analysis in S-Frame, I just go over to here, these little dots, and once you click them, it appears off screen, but you get this menu right here. Basically, what analysis type would you like to do? Well, if we're doing the CSA method, we are doing a linear static analysis. So I can go OK, and after that, you will be greeted with this screen right here. This right here is just a little check to make sure that everything is defined in the models. So as we can see, we have 0 errors, we are good to go. If you have 0 errors, all you have to do after that is just press enter. S-Frame will conduct the analysis, and if we can see over here, we are now in the graphical window. So from here we can look at things like deflection, reaction forces, as well as axial, shear, and bending moment diagrams. So if I were to click the bending moment diagram, as we can see, we are given the bending moment of our structure. But I want to show you guys something really quick, and that is right here, our reaction tools. Remember, I said that since our frame is symmetric, these reaction forces are going to be 0. But as we can see, S-Frame just conducted the analysis, and they're not equal to 0. So I want to mention this a lot because a lot of the students will see that they're not 0. They'll think that maybe something is wrong. And in the worst case scenario, they will add these reaction forces to the translational analysis, which is incorrect. So now you guys may be wondering, hey Clayton, you said they were 0, but they're not equal to 0. Why are these non-zero? Well, if we're dealing with a symmetric frame and we want to prevent sway, then we actually have to add the rollers at the line of symmetry of our frame. In this case, it'd be right here down the center. Since I put them at one end, these reaction forces are actually picking up some axial deformations of our frame, and we actually don't want that to happen. So again, the most common mistake that'll happen with students is they will take these reaction forces and add them to the translational analysis, even though that's incorrect. Now you guys are saying, okay, well, if it's incorrect, how do I prove that these reaction forces are indeed equal to 0? Well, I can go back to my geometry, and instead of having my rollers at the side of the frame, I can add the rollers right down the line of symmetry. So the first thing I'm going to do is I'm going to remove these 2 rollers. Again, I can do that by holding Control and highlighting them, so they now disappeared. And then what I'm going to do is I'm going to add the rollers to the midspan of these 2 members. Now to do that, I need to actually have a joint in these 2 members, which I don't currently have. So what I'm going to do is I'm going to go back to the member definition tool. I'm going to hold Control and highlight these 2 members. Again, that'll remove them. Oop, got to go the other way. And then I'm going to define the member as actually 2 separate members rigidly connected. So I'm going to go back to my one joint tool. And remember, before our member was 10.5 meters long. So I'm going to do half of the member, which is 5.25 in the positive X direction. I go OK, and I can just click twice to create the same member as I did before, but now it has that joint in between. The key thing to keep in mind is once I've deleted this member, its sectional properties are now gone, as well as any loading that I applied. So what I would need to do is I need to come down to my sectional properties. By default, it always applies the first one. In this case, we got lucky because the first one is our beam properties, so we're good to go. But if I were to come down to the load tab, which is down here, as we can see, our loading is now gone. So I have to reapply the negative 45 to the top. I have to apply the negative 55 to the bottom. So I go OK. As we can see, our loading is now in. But again, the whole goal here was I wanted to add those lateral rollers to the center. So I got my lateral roller, I can click OK, and I can highlight them to add my rollers down the symmetric line of our frame. Now if I were to conduct the analysis, again, same procedure as before, We are keeping it linear static. I can go OK. As we can see, when I now examine the reaction forces, they're actually equal to 0. I'll toggle on my reaction forces. So as we can see, we have our rollers, but they have no force here. It is indeed equal to 0. So again, if you want a symmetric frame, you actually don't need to worry about these rollers because the reaction force is going to be equal to 0. But if you do want to include them on your frame, they have to be down the line of symmetry. Otherwise, you will get some non-zero reaction forces. Now, the whole goal of this gravity load analysis is to determine two things. The first one is these reaction forces, as they will be used in our translation analysis. Luckily for us, they're equal to 0, so we don't need to worry about them. And then the second thing is the design load of our member of interest. So for this particular example, we are interested in this member here and this member here. So what I'm going to do is I would want to isolate those members by going up here, unselecting everything. And then what I would do is I'd click this button right here and I would select the members of interest. So I would want this top member right here. I would highlight it and then I can see its axial load, which we have as negative 461 kilonewtons. And then I would determine its bending moment. As we can see, it starts at 293.3 and it comes down to negative 267.34. I would write those down and then I would move on to the next member. So again, I would unselect everything and then I would select the member beneath it, which is this one right here. And then I can see its axial load, which is negative 1025 kilonewtons. And I can see its bending moment profile. So it starts at negative 145 and goes down linearly to 70. So not too bad at all. This is what we would want from the gravity analysis. Once the gravity analysis is complete, we can go to our translational analysis. So what I would do is I'd go back to my frame and we know that, everything is unselected. Let's just select it back up. For the translational analysis, I want to remove these lateral rollers. They're only used in our gravity analysis. So what I would do is I go back to my support conditions, I would hold Control, and I would highlight these two rollers to basically remove them from the frame. So now I can go down to my loading, and I can define my second loading scenario right here, which is going to be my translational case. Translational. I'll put the AL just for fun. Okay. And as we can see, it removed all of the loads from my structure. If I want to go back to the gravity load case, I can just click this button. As we can see, all of my gravity loads came back, but I'm going to define new loads in my translational load case. Now in the translational load case, we have 2-point loads acting left at these two joints over here. Now the key thing to keep in mind if you're doing this with CSA is that these two loads are actually going to be the summation of three things. The first one is any applied forces. So at the top, we have an applied force of 15 kilonewtons. The second one would be the notional loads, and we calculated those in the hand example. And then the third one is going to be the reaction forces from the gravity analysis. So that's why we conduct the gravity analysis first, is because we need to define those reaction forces in our lateral load analysis. Again, luckily for us, since this was a symmetric frame, we didn't have any reaction forces in the gravity load analysis. So these two loads on these joints are just going to be the summation of applied loads plus our notional loads. So we know that they're going to be 2-point loads. So to define a point load, I can go right here to our joint load button. We know that our forces are going to be acting in the X direction. And then since they're both pointed left, they are going to have a negative magnitude. And then for our top story, we know that it's negative 21.9. Again, that's the 15 plus the notional load. I can go OK and I can apply it. And then for our bottom frame, our bottom story, it was negative 43.4. I can go OK and I can apply it. So again, in our translational load case, we do not have any gravity loads. We just have our lateral loads. And again, these are the summation of our applied loads, notional loads, and reaction forces from the gravity analysis. So with everything applied, I can run the analysis by clicking these two buttons. Pops off screen, as we can see, and we are still keeping it a linear static analysis. So I'm going to go OK. And then S-Frame will conduct the analysis, and it'll give us two things that we want. One of the first things that we want, of course, is going to be the loads of these two members that we're interested in. So I'm going to unselect all. I'm going to select this first member right here and I can determine its axial load, which we can see is 9 kilonewtons in tension, and we can determine its bending moment diagram. So it starts at negative 47.2 and it comes down to 26.5. So that would be for that member up top. If I want the member at the bottom, I can unselect all, or I can hold Control to unselect all and then highlight this member down here. I can find its axial load as 30.1 kilonewtons in tension, and I can find its bending moment starting from 84.1 and coming down linearly to negative 114.8. So these would be the design loads we need for our hand calculations. But another thing that we need in our hand calculations, of course, I'm just going to select everything really quick, is we're also going to need the deflection of the stories. So right here is our 3 internal forces, but if I were to come up to this button right here, we can see the deflection of our frame under these loads. Now right now it doesn't have any values. So if I want to see the deflection of these joints, I can use these 3 buttons right here. So it's going to be horizontal deflection, vertical deflection, and rotation. Of course we want horizontal deflection. So if I were to toggle that on, as we can see, we now have the deflection of each one of these joints. And if I were to go through, I can say, okay, for my first story here, it's going to be the maximum of these deflections, which is going to occur on the right, which is negative 24.1. For our second story, it's going to be the same thing, so I'm going to look at these deflections. As we can see, it also occurs on the very right. But remember in the hand calculations that when we're adding these deflections into our calculations, they are the relative story displacements. So for this second story right here, it would actually be the 37.3 minus 24.1, because we're technically starting right here in our analysis. We're only looking at this little deflection right here. It's not the entire deflection. But at this point here, we are good to go, because from the gravity analysis, we got the bending moment and then the axial force. From the translational analysis, we got our second bending moment and axial force. And in addition, we now have those story deflections. So at this point right here, we actually have everything we need for our hand calculations to determine what those U2 amplification factors are in CSA. But some of you guys may be saying, you know what, Clayton? I don't want to do hand calculations. Hand calculations suck. Is there any way that I could just do the P delta analysis by applying all the loads and letting S-frame do all the heavy lifting? Well, of course. So what I'm going to do is I'm going to go back to my frame, and as we can see in its current state, it's exactly the way we want it. What I can do is I can go down to loads, and I can add a new load case, which I will call the total load case. So I'm going to go total. And in this load case, I can actually apply every load to my frame and have S-frame conduct the P delta analysis for me. So if we look here, by default, it already has my joint load defined, so I can just go OK. I can add it here. We know that for this joint right here, we have the negative 21.9. I can go OK, add that there. But if we are doing a total load analysis, we also have to include the gravity loads. So we know that if I were to go back to my global load, we already have the negative 55 saved. So that was the load for the first story. I can go OK, add it all the way across. And then I can decrease it to negative 45, go OK, and I can now add it to the entire top story. So notice that in this load case, let me just toggle this on too so you guys can see, I'm including everything. One thing to keep in mind, because it doesn't really apply for a symmetrical frame, is that if I were to have reaction forces from the gravity analysis, I do not include them in the P delta analysis. If I'm doing a complete P delta analysis in S-frame, this lateral loading is only going to be our applied loads along with our notional loads. We would not add anything else. So now that we have our complete frame with all of its loading, we can go to the analysis button yet again. But the key here is that instead of doing a linear static analysis, we can now do a P delta static analysis. So we would click this option right here. We would go OK. S-frame would conduct the analysis, and if I were to zoom out, as we can see, we now have our frame analyzed completely using a P delta analysis, which is great for us. So if we wanted to, we can look at the axial force diagram, we can look at the shear force diagram, and we can look at the moment diagram. So if we are looking at those two moments of interest, or those two members of interest, which are right here, what I can do is I can unselect all, just like this. I can highlight these two members that I'm interested in. I can click here and I can highlight these two members that I'm interested in, and I can see their bending moment diagram just like this. So if you want to skip all the hand calculations and just do one analysis, this is the way to go. But yeah, that's it for this video. So I want to thank you guys so much for watching. I hope I helped answer some of your questions. If not, I'm sorry for wasting your time. I hope you all have a wonderful day, and I will see you in the next example video.